Hello, this is a remote-controlled camera car powered by a Raspberry Pi. See in this video how I built that car and how you can build one by yourself. So stay tuned. First I will talk about the mechanical components like the chassis, wheels and motors. Second, the electrical stuff including motor drivers, sensors, camera, power supply and so on. And third, the software that takes control of all these components. So let's start with the most fundamental part, the chassis. You find a big choice of robot car chassis on eBay, but these are either very expensive or have these crappy yellow DC gear motors which let me grow a lot of grey hair. So I decided to build my own chassis and use stepper motors instead, but more on stepper motors later. I made it as simple as possible. I cut a piece of plywood for the base, drilled the holes in and screwed the L-mounts for the motors onto it. Then I installed such a swivel caster that you can buy in any hardware store. And finally I attached the motors. Now we need to somehow fix the wheels to the motors. Select the wheels according to the surface you want the robot to ride on. The more uneven, the bigger the wheels should be. Soft profiled rubber tires have the best grip. These 12mm hex wheels for RC cars are a good choice there. As I couldn't find a suitable adapter to mount them on the motor axis, I designed them in FreeCAD. I don't own a 3D printer, but that's not a problem at all. There are 3D printing companies all around the world. To get a 3D print, all you have to do is upload the mesh file to one of their websites, then specify how many copies you want, double check, then select material, finish and color. You receive your offer immediately, and it's not even expensive. And here is what I finally got after a few days. I glued a threaded rod into the holes on the hexagonal end and pressed the other end over the motor axis. Then I stick the wheels on and secure them with nuts. Like already said, I use stepper motors instead of DC motors. The advantage is that these can be controlled very precisely. In addition, they have a high torque even at low speeds and therefore they do not need a gearbox. As the animation shows, 4 electromagnets in a stepper motor are controlled in such a way that their magnetic fields take the rotor with them. Tinkering with stepper motors is simple. With a driver module like the A4988, the motor goes one step forward whenever we apply a rising edge to its step input. Most stepper motors have 200 steps per revolution, so pressing these buttons 200 times will make one turn. By joining the 3 microstep inputs to low or high, the module will divide the steps into 2, 4, 8 or 16 microsteps. So we get an even finer resolution. I joined all of the 3 microstep pins to the supply voltage to configure the driver module for 16 microsteps per step. That lets the motor run soft and smoothly. And with 16 multiplied by 200 steps per turn, we need 3200 pulses to go around once. This means that we need a frequency of 3200 Hz for 1 round per second. Toggling the direction pin makes the little guy here ride the other way around. With a circumference of 28 cm and a desired maximum speed of 5 km per hour, the motor has to rotate at approximately up to 5 revolutions per second. This requires variable frequencies up to 16 kHz. I want to generate these frequencies and the direction signal with a Raspberry Pi. In the first shot I tried this with the GPIO0 library, which can provide variable frequencies. But it turned out that the frequencies that I got were quite wobbly and inaccurate. This is due to the fact that GPIO 0 generates the frequencies in software. The superior method is to utilize the hardware PWM timers. These run independently from the CPU and give us a nice and stable output. I used the PyGPIO library for this. Now let's take a look at the power supply. That's a bit tricky because we need two supply voltages, 5 volt and 12 volt. The 5 volt are needed by the Raspberry Pi and the 12 volt by the stepper motors and their drivers. I get the 12 volt motor voltage out of a quick charge capable power bank. A step down converter converts it down to 5 volt. And here is a prototype board with an NE555 timer based circuit that switches the power bank to 12 volt and a step down converter for the 5 volt. Of course you can also just use two batteries to make things easier. It's up to you. Now we can mount the electronics on the chassis. I prepare two more sheets of plywood where I put bolts in. Then I screw them onto the chassis. On top of that I put the perf board with the power supply and then the stepper motor drivers. Then I fix the power bank with a few drops of hot glue. Of course, also double-sided duct tape will do the job. Now I screw the Raspberry Pi on. You can use any Raspberry Pi for this project. I used the Raspberry Pi 4B here, but it also works fine with other Pi models. And here comes an ultrasonic proximity sensor. Unfortunately, this works with 5 volt TTL input and output levels, while the Raspberry Pi GPIOs are rated for 3.3 volt. This makes a level shifter module necessary. The proximity sensor will stop the car immediately if it gets closer than 30 cm to an obstacle. The robot car also gets a camera that is mounted on a piece of plywood that is fixed between two flexible strips of thin copper sheet. This camera has an automatic IR cut filter and two infrared LED headlights for night vision, so it can see even in complete darkness. I applied a small hack to them that allows me to control their brightness by software. With a small cable harness, I join everything to the Raspberry Pi pin header. Plugged in the motors. And the ribbon cable for the camera. Now the assembly is done and I will go ahead and install the software now. The robot is remote controlled by a dynamic HTML page provided by the Flask framework. This sends an MJPEG stream generated by the camera to an HTML page. All the backend software is written in Python. When you hover the mouse over the image or touch it on a mobile device, the control widgets show up. And now you can move the robot forward, back, turn left, alright. All these commands are issued by scripts which are executed in the scope of the browser. The HTML page uses MQTT over WebSockets to communicate with the Raspberry Pi. Mosquitto is used as broker there. You can take a look into the video description if you want to learn more about the details or make one by yourself. Do you have any ideas for new functions and features? Then let me know in the comment section down below. I always appreciate your suggestions. And if you like this video, please give it a thumbs up. And don't forget to subscribe and enable notifications so you won't miss any news. Thanks for watching. See you in my next video.